Just looking at the back of the room here, just to give a wave to our AV desk, because we're live streaming this session. So these Insight stages will be available live on YouTube Live, as well as Australia's Mining Monthly. So to start, we've got Caterpillar, semi-autonomous dozers pushing the limits, and we've got Simon Rock from Westrac talking us through that. So welcome, Simon.
Thank you very much. I'll flick through this very quickly. We've only got 10 minutes and it's obviously a very large topic which could take hours for those who are interested. The SATS program is part of our MineStar autonomous suite of programs and features both hardware and software. And again, I'm flicking through this very quickly and catch up with people later if they'd like to talk through some of these topics. We'll get to the meat of the thing. The dozer system that we have on offer is a scalable system. It functions from the basic system as a remote control. This is not new technology. We've had remote control machines underground and in the field for many, many years. The next stage up is a remote station. This is a simulated dozer setup, operator setup, where one operator can control a remote dozer. These have been around for a while. You're seeing it takes the operator out of the cab, puts them into a safe environment. Then we move up with a semi-autonomous system where one operator is controlling multiple dozers, and those dozers have some inbuilt smarts, and we'll go through that shortly. The remote station and the semi-autonomous are non-line of sight, so this operator does not have to be on the mine site. They can be wherever you want to be, especially with the internet these days. And these remote station situations, these are not an add-on. These are a factory specified bit of gear. So you can order it from Westrac or your local cat dealer as a factory option. So what is SATS? SATS is a semi-autonomous tractor system. It's a Caterpillar product for the remote operation and automation of our D11 dozers. Currently using them in bulk push scenarios. SATS allows for the semi-autonomous operation of up to 4 dozers by one operator. So one operator sitting anywhere in the world can control four dozers working out in the field, and this is done through a remote trailer or office situation there. And you can see there's only 3 in that example, but they're out in the field working. So why do we have SATS? Of course, you're taking the operator out of the cab. Out of the cab means it's safer. You haven't got an operator being bounced around, shaken, and people were in the earlier presentation inside. You saw some video of a truck driver in a pit. Dozing is a very rough operation for people. You know, body's getting shaken. You wonder why people slow down a bit in the dozer. If you've been in one on a hard dig, hard ripping, you'd understand. Cost, you're increasing the utilisation and availability. The dozer's not stopping for smoko to get out and have a leak, just to rest because they've had the life shaken out of them. Another one, of course, is productivity. Because the dozer is being controlled by a computer, it's consistent and reliable in terms of its performance. It will do the same thing over and over again, whereas an operator will be driving backwards and forwards, might look out the window, look down at their iPhone, just loses concentration. Obviously a computer doesn't lose concentration. So how does SATS dozing work? We have a dozer, of course. We add some smarts to that dozer, an onboard computer, cameras, high precision GPS, so we know where the dozer is in 3 axes. Additional switching, so the SATS can be turned on and off as you get on and off the dozer. We need a network infrastructure, so the dozer can talk back to the command there, high precision, so we know where we are, XYZ. some mode lights to tell people around it what the dozer, what mode it's in. Is it in semi-autonomous mode? Is it just in normal operator mode? We have some cameras on board. Cameras allow the operator to see in front, behind, and these days with the 360-degree cameras, we can get a 360-degree simulated view of what's happening around that dozer. And of course some ground level service switching. So as the operator gets off the dozer, he or she can switch it to autonomous mode. A little bit of a schematic there, just showing 4 dozers, some repeater stations. Of course the network infrastructure is driven by site requirements, communication towers, and of course your remote station and servers. All the normal sort of things, and these are all, of course, driven by site requirements. We talk about the control room. There's an example of a truck-mounted control room. So in that situation on a mine site, it could drive around and follow the operation round if you wanted to. The lovely ATCO shed that many of us will have experienced out of mine sites. Again, it can be transportable, or it can be in any location that you need it to be in, on-site or off-site. And of course, a control station itself. The control station mimics a dozer setup. So an operator in that control station, if they've been driving a dozer for years, they've picked them up, put them in a control room. The controls are the same. They're identical controls. So there's no retraining of the operator for that control station. And of course multiple monitors to give them enough vision around the machine. And our lovely shiny yellow dozer with cameras on it. Operation. So in operation, a dozer operator will take control of a dozer using the cameras. He'll position that dozer in the work area and assign it to a task. That task will be then validated while the operator controls it through one pass of that to make sure it's all working, the levels are correct, and then switching over to autonomous mode. Then using the onboard smarts, the dozer will then proceed backwards and forwards doing that bulk push, working within that area, while the operator then can switch over to another machine and set that one up and get that one working. So using that system of assigning a task and then rolling it in, the operator, initially we thought 3 dozers would be enough. We see operators now controlling 4 dozers very effectively. The target there, of course, is having a very safe and highly productive operation. Those dozers, while they're moving backwards and forwards, are productive. They're following a computer algorithm that's been honed and refined to be the most productive it can. Of course, productivity benefits, other than getting the operator out and having them safer, which should always be our first concern, is we have a decreased fatigue. So the operator's not bouncing around. They're in a nice air-conditioned stationary room, more productive. The dozers can work steeper angles, but you don't have that operator perception. Reduced shift change times. You don't have to run an operator out to the dozers and swap them over. He or she gets out of the chair, moves over, and the next operator gets in. So you've got very little shift change time. Immediate operations after blasting. Traditionally, a dozer has to walk out of a blast zone to avoid any risk to the operator. Becomes a commercialised decision how far then you need to move away to keep the dozer safe, because you haven't got an operator there. No operator makes it a lot easier. Dozer high wall cleaning, both the remote and the remote control and the non-line of sight type remote operations as well, you can get right in under the high wall because you don't have an operator in the cab. So there's a huge advantage there to the remote operation of a dozer. A very quick overview. There's obviously a lot that goes into a semi-autonomous tractor system. The CAT command It's a proven technology with the remote control. It's a stock item from the factory, the remote control machines. It's not an add-on, it's not an aftermarket. It's a factory-supported, dealer-supported system. We have the underlying technologies and have to deliver this system. We've got the runs on the board, and we're refining those as we move forward. So hopefully we'll continue to improve the systems and develop better, more productive algorithms. Any questions? I've moved that quickly that you've all got 100% take up. Great.
What's the ballpark figure for the hardware installation on the vehicle?
The hardware installation, I'll take that offline. A lot of the work we do, depending on what model dozer you have, what's already on it, you can buy the dozers at different levels as they come out of the factory. Some require more work, obviously. Some already have terrain if you've got GPS on them. So it's a, yeah, we need to assess what the dozer has on it already. And it's like the network infrastructure, depending on the mine site, depending on what's already there, will affect what as you can imagine, with video you are requiring high capacity network infrastructure to stream and multiple cameras across the site. So I'll catch up with you later and we can talk about that one.
Simon, is there any interactions between the dozers pushing to central points? So, for instance, of course, or stockpiles or dozer traps or things like that?
With the system, because it's using terrain, you can geofence and there is interaction. They know where they are. They're high precision GPS, so we're talking small differences in accuracy, a 10 centimetre accuracy. So there is that built into the system, so they know where they are with the proximity awareness. So the use of the remote control situation for stockpiles and that sort of thing is a bigger factor. A lot of companies are looking at that because you can take that dozer operator out of the dozer, put him in the control, or she in the control room, and while you still may have a problem with a hang-up, if you don't have an operator in that dozer, if the dozer falls into a hang-up, well, you've got no safety issue in terms of a human safety issue. So it takes that away. So our mine planning has to develop, and one of the earlier presentations was talking about mine planning and autonomy. There's a huge difference. It's not just whack a bit of technology in. You've really got to rethink and go, okay, what can we do now to improve? Where can we gain with our mine planning? With the autonomy systems, some operations that are using the SAT systems have had to rethink how they do their mine planning. You've got to have dirt in front of the dozer. If there's no dirt, there's nothing to push. So, you know, and they like consistent tasks, not do a little bit here, a little bit there. Give them a good task that they can push for hours. That's where you get your big savings. So you need to design around that. Any other questions? No worries. Thank you very much.
Thanks very much, Simon. And as I said earlier, all these presentations are available online as a video feed on demand. So after this event, you're welcome to go back and watch these presentations in their entirety. Our next speaker is Shahram Tafazoli from Motion Metrics. Shahram is the president and CEO, and he'll be talking to us about how deep learning can revolutionize blast optimization. So welcome, Shahram. Thank you.
Thank you very much. Good morning, everyone. Thanks a lot to Future of Mining. Excited to be here and presenting after Caterpillar. Really enjoyed the talk. So I'm going to be covering how at Motion Metrics we use artificial intelligence to optimize or revolutionize blast optimization. So my presentation first about the problem. What's blast optimization? I'll look at it from the particle size distribution point of view, PSD. And how do we propose analyzing? PSD inside the shovel buckets and how it can be used to optimize blasting, which can be the least expensive part of the comminution. Then we'll talk a little bit about the solution, how it works. It has 3 AI components. One is on the embedded system, how do we choose the best images from the shovel's digging cycle. Second part is how on the cloud we choose the bucket and the region of interest. And the third one is how we do segmentation using AI. At the end, I show you real field results from different shovels around the world from the logs that I have been collecting in the last few months. So blast optimization. Particle size distribution of the blasted material is very key to optimization of the blast. So as you can see, that's the typical open pit mine. The focus of my talk is going to be on the mining shovel. So you got a mining shovel. How do we measure the rock sizes inside that? So it can be a hydraulic shovel. You can see it has a big rock on the left, top left. It can be a P&H cable shovel, which over there you see one rock, a lot of fines, Bucyrus, or it could be a backhoe, which is quite often used in Australia. So very clear problem definition. What's image-based particle size distribution? You take a picture, you trace the rocks. It could be human-based, it could be automatic. I'll talk about that. And you apply scaling. You can see in this image, they are using basketballs for that scaling with some simplification process. So, and then you get particle size distribution and fit things. So in terms of scaling, you could either use those known objects. In the middle, I'm using the bucket width, which is the typical for our application. In the case of on the right-hand side, you see a conveyor belt where we are assuming the camera is a fixed distance, let's say 2 meters, or we can use laser. In the bottom, you see a stereo imaging device that we have devised in motion metrics using 3D imaging, so no assumption whatsoever. So the bottom one, the one in green, 3D imaging addresses both safety and accuracy concern. That's the best approach, but I'm not going to talk about it. I'm not going to talk about the left one, the right, or how good that is. This is a simpler problem of how do I do rock segmentation inside the shovel bucket. To go from that, this focus of this talk, to that, and then have the particle size distribution. So the solution, as I mentioned, has 3 parts. One is on the embedded part. So you have a camera on the mining shovel. The embedded part has one responsibility. Take a good image, send it to the cloud, either right away or a bit later, because this is not mission critical. The 2 other parts, one is about region of interest. Let's find the bucket in the image. Let's find where the material is. And the third part, let's do segmentation of rocks. I'm going to explain how we are using AI to address all 3 efficiently and in an automatic manner. This is supervised deep learning. What you see here is different images from a hydraulic shovel and a Bucyrus shovel. We have developed tools in-house which humans go spend time on each image of a bucket to define whether it's empty or full, different colors for the teeth, background, sides of the bucket, and all that. This is essentially used in the AI network to train the networks in order to do this automatically in the world of machine vision, machine learning. So the embedded processing, because the embedded processor, we are busy, we are doing missing tools detection and a lot of other tasks, we have very limited resource. So the algorithm, this is what it does. You see the image on the left, input image, that's a nice one, full bucket. Algorithm does 2 things. Number 2, map of the movement of each pixel between 2 subsequent images. So if you have a full bucket and you're swinging, the foreground is fixed, the background is moving, we use optical image flow to get that. The right-hand side, we use AI to define probability of any pixel in the image corresponding to a suitable for fragmentation. And that is coming from that supervised learning I talked earlier. So whenever those 2 have a match, we say, oh, this is a good image. You see the right-hand side. We say send it to the cloud. When you are in the cloud, in the Amazon Web Services or Azure, you have the world at your disposal. You can use any algorithm you want. You can use tons of libraries. It's cheap. You don't have the limited resources on the mining shovel. So this is the first process on the embedded side. Let's talk about on the cloud. The feature map extractor we are using is taken from the state of the art where Google Photos, etc., uses an image to decide whether there's eyes, there's nose, there's lips. In our case, it's not as exciting. We are using the image to see if is there a bucket, is it full, is it suitable, is there shadow in the image, which is not good. So very similar approach, but totally different application. So we have implemented that. Over here on the cloud, we use many rectangles, and to find out which one corresponds on the left side to a bucket, which one corresponds to a full bucket suitable for segmentation. Whenever we have a match, this could be about 10,000 different matches we are doing. On the cloud, not a problem, cheap. The result is saying, OK, suitable, let's go to the next stage. Over here, you can see exactly that. That image has been chosen, and then next AI decides, say, I'm going to use vertices to find where the region of interest is, but we don't want to go too many vertices because it's going to be hard for humans to correct. So we say with a maximum 12 points, where is the region of interest? And what you are seeing here is the result of AI. So learning a lot from human labeling. So I promised to show you field results, and here we go. This is an African mine, a hydraulic shovel. The image taken earlier is actually, this is very new, 24th of March. So you can see that's the result of AI. So I'll go back a little bit. Perfectly got that big rock, small rocks. The blue means fines. If you look at the right-hand side, that's the distribution. The green area is where is acceptable sizes happening. The red is like you have oversized, you see those big rocks, and the blue is undersized. So this is an example on a hydraulic shovel. Move on. Same hydraulic shovel. You see the material is kind of tilted. This is what AI decided that is good full bucket. And just let me go back. Pretty good. And this is something for about 15 years we have tried to solve it, and finally AI is being able to address. So previously we used conventional image processing with a lot of challenges. I didn't talk much about segmentation using AI, but what we have done, we have thousands of images from shovels, from portable device, from on the conveyor belt, which we have asked humans to go and trace the rocks. And a typical big image can take 4 hours for a person to go and trace it. With AI, we are talking about seconds. And there are cases we are seeing the results can even beat. And it's a very boring task. It's very time-consuming and all that. So here's another one, African gold mine, hydraulic shovel again. This is either in size or fines. You can see on the right-hand side. Image was taken 21st of February. And by the way, these logs are automatically coming to our webpage from the subscriptions we have around the world. Since the beginning of my talk to now, probably 200 more images came to our webpage and all get analyzed in terms of rock sizes. Look at this one. You have a big rock. That's the P100. You can see more than 1 meter there. And good amount in the range and some below. And remember, this is one single image. Roughly every 5 minutes, ideally, we want to get one image. So you can get a good representative images, and you don't need to send anybody to the field to do the dangerous job or somebody putting basketballs, take picture, come back. The shovel is digging, we automatically get these happening. African gold mine, hydraulic shovel. You see this is a lot of fines and a couple of rocks. Chile copper mine is a P&H cable shovel. For example, you can see, I don't want to claim AI is doing a perfect job. You see there's shortcomings there, right? But the key thing in that image, if I can go back, we avoided the teeth because our old algorithm, a lot of times the teeth were getting into it. This is another image from Chile mine. Again, it's quite good. Remember, it's using the size of the bucket for scaling. If the bucket is 5 meters, we'll use that. And this is a Bucyrus shovel. It did a decent job. I especially chose some images where it could be some missegmentation. You can see some of these. So what we have done in motion metrics, you see that bottom on the right, which has a pencil. We have developed correction tools. So because on the shovel, typically you get, 20 images per day, you can have humans go and correct what the AI made a mistake. So we call that, instead of AI, which is artificial intelligence, we call it intelligence augmented. So a human goes where AI came short and address that. So IA is used everywhere today. And at Motion Metrics, we are using it in the mining application. And I'm not afraid of mentioning it because AI, as much as everybody is saying is good and all that, it has its shortcomings. So one more Chilean copper mine. This is back in February. So quick conclusion, particle size distribution inside the shovel bucket is one of the best indications of how good was the blasting. You can take that and say, let's improve, let's have smaller rock sizes or bigger, which is that the blast engineer's expertise. So as you saw, we are employing AI in every stage, from choosing a good image to send to the cloud, to choosing the size, delineating the bucket, choosing the region of interest, and segmentation. Out of all of these, I have to mention, segmentation is the hardest job. For 15 years, the problem started when in Africa, I had the first system, the camera. The mine engineer looked at the video and said, Shahram, can you use that to tell me what the rock segmentation is? You know what? Until that day, I didn't know what rock fragmentation meant. Because my background is mining, zero. So, but since then, we have been working in this problem. And finally, with bringing AI into it, after 3 years of challenging, we have been able to solve it. I showed the system performance, so field results, showed the effectiveness. We are 100% there, not there yet. Like on the backhoe, we are having some challenges, so we are updating the networks. But here's the advantage. It's good to take away from this talk. In the old days, you will have an algorithm, you will get engineers to make it better. In the modern day, you say, oh, do I have a bad result? Let's get it properly labeled by a human. Let's update the network and optimization. Next day, you have a new version of software. That wasn't possible before. So, and thanks for coming to my talk. We have a booth number 13. Mark Mukhija, he's our Australia manager. He's here. And happy to answer any question. We are kind of eating into the talk, so my apologies.
We're going to maybe just cut this a little
Okay.
short.
Yep.
We've got some other sessions about to start.
Right,
So, as Shahram said, they have an expo space here. So, any questions,
Yes.
perhaps
Please.
visit your stand, and
Yep.
you'd be happy to help out.
Thank you very much. Thanks, everyone. Thank you.
We're about to split into the work streams, so there's 3 sessions to choose from. You can make your way out to those now. Thank you.